In this video, we'll talk about the gaseous state of matter in particular. So now we know that solid, liquid and gas are the most common states of matter. And in fact, the gaseous state is the simplest form of matter and we are surrounded by an ocean of gases. And the reason we say that the gaseous state is the simplest form of matter is because in this state, atoms and or molecules have very weak forces of attraction amongst themselves. These molecules are pretty much free to move around without feeling the influence of other atoms or other molecules. So now we need to constantly remind ourselves that these intermolecular forces are not completely absent in gases. They're relatively weak when you compare it to solids and liquids, but they're not completely absent. Although you will see that when we go over the section of ideal gas laws, we're going to make a huge assumption that these intermolecular forces do not exist in ideal gases. But in real gases, that's not the case. So if you look at the solids and on the other extreme, atoms here have very, very strong intermolecular interatomic forces of attraction. They are all locked in certain positions and all atoms are close packed, and hence solids have very high densities because of that. They also have definite volume and a definite shape, and they are rigid and incompressible. They don't yield to pressure. So now liquids are relatively less dense, they're less closely packed. They have a definite volume, but they do not have a definite shape. They just take the shape of their container. They still do have a decently strong interatomic and intermolecular forces of attraction, not as strong as in solids, but here atoms and molecules have enough freedom to actually move around and slide past one another. And like solids, liquids are incompressible as well. Now gases, they have extremely low densities. They have no definite shape and no definite volume. So even a small amount of gas can actually fill an entire room if you want. And most importantly, gases are compressible. Compressible to a great degree, in fact. So what that means is that they yield to pressure, meaning you can apply pressure and compress or reduce the volume of a gas, which is impossible with a solid or a liquid. So if we take a quick look at the periodic table, you'll see that there are only a total of 11 elements that exist as gases under normal conditions. And by normal conditions, we mean room temperature, that's 25 degrees C and 1 atmosphere. So along with hydrogen that's on the left end of the table, you have all these gases. The rest of the gases are on the other end. The noble gases are the ones that exist as monoatomic gases, whereas the others in pink here are all, diatomic, or oxygen can actually exist as O3, ozone as well. But that's it. There are only a total of 11 elements that exist as gases. Then you have mercury and bromine that are liquids at room temperature, and the rest of the periodic table is all solids. So of course, you have gases that are compounds, which are many, many, many more that we find all around us. But these are the ones that exist in their elemental form. So before we move on to discuss the general laws that govern the behavior of gases, I'd like to take a few minutes here to quickly give you an intuitive feel to what gas pressure actually means and how we can measure it. And we know that pressure is force per unit area, and that is Newton per meter square, which is a Pascal. These are the SI units. So if you take a gas enclosed in a sealed container, or let's say in this case, let's just take a balloon. So at any point of time, these gas molecules are moving around freely. There are billions, millions and billions of gas molecules that are constantly colliding with one another and also colliding with the skin of the balloon on the inside. And each one of these collisions will have an associated force of impact, whether they're colliding with one another or they're colliding with the surface of the balloon. Now it's impossible for us to actually single out one of these gas molecules and measure force of impact of a single collision, because the force of impact of a single collision will be too small for us to measure. But remember, there are billions and billions of gas molecules in this volume of the balloon, and if you consider the thousands of billions of collisions each second with the skin of the balloon here, this large number of impacts of gas molecules actually exerts a considerable force on the surface of the balloon. So if you take that force per unit area, you get gas pressure. So you have atoms and molecules constantly bombarding with the skin of the balloon, and you have millions and billions of such collisions happening every second. So if you look at it macroscopically, there is a considerable finite amount of force of impact that these molecules exert on the skin of the balloon per second at any given point of time. So that is a measure of the gas pressure, the resultant gas pressure. So an important thing to remember here is the direction of the resultant gas pressure force here is always perpendicular to the surface of the balloon. So it's always perpendicular. The resultant is always perpendicular to the surface of the balloon. So at any point you take, the resultant force is always going to be perpendicular to the tangent drawn at that point. So now let me clarify what we mean by that. So why do we say that this direction is always perpendicular? So there are collisions happening in multiple directions at a given point, and at every point here the pressure exerted is the same. The resultant pressure exerted is the same. Let's say we call it PB. Let's say a single location on the skin of the balloon. Let's say it is this location here, and you're looking at all the collisions that are happening at that single location at a given point of time, and whatever happens at this location is pretty much the same story for all the other locations on the balloon. So this point will be sort of representative of whatever is happening at all points on the balloon. So let's single out one particular collision here. Let's say collision happening in this direction. So this is clearly an oblique collision. It's not perpendicular to the surface of the balloon at that location. So what I want to claim here is, for every single collision like this that is not perpendicular, you have a collision in this direction, because imagine there are thousands and thousands of collisions happening at this location at any given point of time. So for every direction like this, you can actually find the direction of impact in this way. So if you can resolve this particular force of impact in two directions, one direction that is perpendicular to the surface of the balloon at that location, and that is parallel to that to the tangent drawn here. So you can do that the same thing here as well at that point. So if you take a collision this way, so you can have so the components drawn are, this is going to be perpendicular to the surface of the balloon, that is parallel, and similarly you can so for this you can have an equal and opposite sort of impact, wherein again you can draw a parallel and perpendicular components. So these two are going to cancel, and the resultant is going to be 0 in that direction. But what adds up are the components that are perpendicular to the surface of the balloon at that point. So you get the idea. So that is why we say that the resultant gas pressure force is at any point on the interiors of the balloon is going to be perpendicular to the balloon at that point. So remember, this is because you have many collisions happening. So for any particular value of a force of impact and the direction that you select, you will have another force of impact at that point, because there are so many collisions. You will find at least one collision that is going to be very similar but opposite in direction this way, so that their components add up and give a resultant pressure force in the direction perpendicular to the surface of the balloon. So that is the story on the inside of the balloon, and PB is your resultant pressure due to the gas present on the inside. Now, there's not only gas inside the balloon exerting pressure from the inside, but there's also gas or air on the outside, because this balloon is sitting out in the open, right? So there is also gas on the outside, air on the outside, that's exerting pressure on the outside surface of the balloon. So something like that. Again, the resultant direction of this pressure is perpendicular to the surface of the balloon. So let's call this the P atmosphere. So now, as long as the balloon is sitting outside in this, out in the open, the outside pressure is going to be constant, and that pressure is not going to change as long as the balloon is not moving anywhere. Now, if the pressure on the inside is equal to the pressure on the outside, which is the atmospheric pressure, then the balloon will actually stay put. It's not going to do anything. It's not going to blow up or change its volume. And remember, the pressure is inside is directly proportional to the rate at which the gas molecules are colliding with the surface. That is the number of gas molecules bombarding with the skin on the inside in 1 second. So what can you do to blow up this balloon further? So you can do that if we increase the gas pressure on the inside. So if PB were at some point greater than P atmosphere, then there is obviously an imbalance in the forces exerted from the inside and forces exerted from the outside. So there is a resultant force that acts outwards if the pressure inside is higher, and that will cause the balloon to stretch, and the balloon will increase in volume. So it will increase in volume. And how much will that increase be, and how much will the balloon bloat up? That will depend on, when the pressure inside falls back to the pressure equal to the outside, that is the P atmosphere. So the volume will go on increasing until PB becomes equal to P atmosphere again. So what you're seeing here essentially is that as the volume of the gas is going up, the pressure inside actually falls and back to the P atmosphere. So keep that thought. We're going to get back to this relationship or this trend in a subsequent video. So in what ways can you actually increase the pressure on the inside? So we can increase the pressure by increasing the rate at which the gas molecules are bombarding with the skin of the balloon. So, and how do we increase this rate at which gas molecules are bombarding with the balloon? Either we blow more gas or air into the balloon. So you'll have more gas molecules inside. The more the gas molecules there are, the more collisions you'll have, and hence the pressure inside will go up. Another way to increase the pressure inside will be to increase the temperature of the gas inside. So what happens is, by increasing the temperature, you impart greater kinetic energy to these gas molecules. So they are all of a sudden moving around faster with higher velocities, colliding, at a faster rate. And as a result, there are again more collisions per second or per unit time. So again, the pressure then will go up. So all these observations that we are making here make sense intuitively, right? Because you will see in the subsequent videos how very similar observations like these made scientists in the past come up with some gas laws that actually govern the behavior of all the gases. And we've talked so much about gas pressure now. In the next video, what I'm going to do is I'll tell you how you can actually measure this pressure using a few simple devices.